Welcome back, design junkies, to Mechanical Engineering Made Simple. Hey, if what we cover here brings you value, do me a favor and help support the show with a like, a follow, or just leave a comment below. It really helps. All right, let's dive right into what is honestly one of the trickiest areas in our field, designing centrifugal compressors and radial turbines that actually hold up. We're going to map out the whole landscape today. We'll start with the biggest headaches that make these designs fail. Then we're going to bust some common myths that trip up even seasoned pros. After that, I'll walk you through a solid design process so you don't fall into the same traps. And finally, we'll talk about how to take a good design and really push it to be fully optimized.
So you know the feeling, right? It's that classic engineering nightmare. Your design looks absolutely perfect on the computer, flawless in the simulation. But then it fails, and fails spectacularly out in the real world. Why does this happen so often? Well, it usually boils down to a few key culprits, these silent killers of performance.
Let's name them. These are the big ones, the primary failure nodes that every single one of us has to have on our radar from day one.
And here are the usual suspects: cavitation, choking, and just sheer mechanical stress. Think of cavitation like thousands of tiny, violent explosions happening inside your pump as vapor bubbles form and collapse. Choking, well, that's basically a traffic jam for your fluid. It hits the speed of sound and just can't go any faster. And of course, the incredible mechanical stress from spinning these components at tens of thousands of RPM. These three are the recurring nightmares for any turbomachinery designer.
Now, why do we keep falling into these traps? A lot of the time, the root of the problem actually stems from a few fundamental misunderstandings. It's that huge gap between the clean, simple world of textbook theory and the messy, complicated physics of the real world.
All right, so the first and honestly the biggest myth we've got to bust right now is this idea of ideal flow. Textbooks love it because it makes the math easy, but in reality, the fluid is way more rebellious than that. It doesn't just politely follow the curve of the impeller vanes. It tends to slip off. This phenomenon, called slip, is a huge deal because it directly cuts down on the energy you can transfer, and that torpedoes your performance.
Okay, so if the textbook model is out, what do we do? How do we design for this messy reality? Simple. We quantify it. We give this imperfection a number. And we do that using something called the slip factor. This is the crucial correction that lets us connect our neat theoretical calculations back to how the machine will actually behave.
And you're going to love this part. For radial vanes, we can start with this beautifully simple rule of thumb. The slip factor, sigma s, is approximately 1 minus 2 divided by z, where z is just the number of vanes you have. I mean, look at that. It might seem too simple, but this little formula is an incredibly powerful starting point that gets you surprisingly close to what you'll see in real-world tests.
Okay, get ready for another one that goes against everything you might have learned in class. We're always taught that for the best efficiency, the flow should enter perfectly parallel to the blades, right? Zero incidence. But here's the kicker. For inward flow radial turbines, actual research shows the sweet spot, the optimum angle for peak efficiency, can be as high as 30 or even 40 degrees. So if you're chasing that perfect zero incidence angle, you might actually be kneecapping your own design's performance.
All right, so we've debunked some of the big misconceptions. Now, let's get practical. Let's build a better design process, a framework that actually accounts for all this real-world mess right from the get-go.
Look, a truly robust design process follows a really clear path. Step 1, you've got to optimize the inlet to get the fluid in cleanly and avoid problems like cavitation. Step 2, you immediately apply that slip factor to correct for the fluid's imperfect behavior. Step 3, you go on a hunt for every single way you might lose energy. And finally, step 4, you carefully design the exit, the diffuser or exducer, to recover every last bit of useful kinetic energy and turn it into pressure.
And listen, when I say quantify losses, I'm not just talking about a little bit of friction. No, we have to be detectives here. We're talking about energy that's literally leaking over the blade tips, the turbulence you get when you're running at off-design conditions, the drag on the back of the impeller disc, and of course, all that valuable kinetic energy you're just dumping out the exhaust if your exit design isn't up to snuff. All right, so you've followed the process, you've got a design that works, it's functional, but how do we take it to the next level? How do we get from just good enough to truly optimized? Well, the secret is all about understanding and making smart trade-offs.
This is a classic dilemma right here, choosing the vanes for a compressor. You could go with radial vanes. They're great for getting a high pressure ratio at a certain speed, and the stress levels are a bit lower, but the trade-off is a pretty narrow operating range. On the other hand,
Backswept vanes give you a much wider, more forgiving range before you hit problems, but you have to accept a lower pressure ratio at that same speed and deal with higher blade stresses. It's always a trade-off.
Okay, but what about the really big decisions? Like, should this even be a radial turbine or an axial one? How do you even start to make that call? Well, there's this incredible, almost secret weapon parameter called specific speed. It's not about raw power or RPMs. Think of it as a universal matchmaking tool. It takes the flow rate you need, the pressure rise you want, and it tells you what shape of machine will be the most efficient for that specific job.
And this chart right here, this shows you exactly why it's such a game changer. Look at this. Each type of turbine has its own sweet spot, its own zone where it really shines. Axial turbines are the absolute champs at high specific speeds. But look at that middle range. A well-designed inward flow radial turbine isn't just a good option, it can be just as efficient, or sometimes even more so. Specific speed guides you to the right tool for the job every time.
Okay, to wrap this all up, let's quickly tackle a few of the most common questions and points of confusion that always seem to come up when we talk about this stuff.
First one up is a classic. Pump, fan, compressor. People tend to throw these words around like they're the same thing, but in our world, from an engineering perspective, the dividing line is actually crystal clear.
It all boils down to one simple thing: compressibility. A pump moves liquid, easy. A fan moves gas, but only gives it a small pressure bump, not enough to really change its density. A compressor, though, that's when you start squeezing the gas hard enough to matter. And the magic number is 1.05. If the density of the gas increases by more than 5% from the inlet to the outlet, congratulations, you've officially got yourself a compressor.
And this next question is a great one. Why do we see radial turbines all over the place in automotive turbochargers, but you never see them in a big jet engine? Well, this comes full circle right back to those design advantages and trade-offs we were just talking about. Here's the bottom line. A radial turbine is a compact little beast. It's incredibly rugged and crams a huge amount of work into a tiny package, which is exactly what you need for the high-pressure, high-temp, cramped environment of a car's turbocharger. But a modern jet engine needs to swallow a ridiculously huge amount of air. For that massive flow rate, the multi-stage axial design is king. It's simply the right tool for a completely different job.
So that's the key, isn't it? Once you really start to understand these real-world constraints, these physical limitations and trade-offs, you stop just designing on paper. You start engineering for reality. So the only question left is, with these tools in your pocket, what are you going to go out and design next? If you got something useful out of today's explainer, hit that follow button and drop a like. It really helps grow the show and keeps the engineering knowledge flowing.